Hello everyone, in this video, we're going to review integration by trigonometric substitution. This technique is usually used when we encounter integrals that have radicals in them, in particular one of these three forms or cases. Just note that encountering a radical in your integral does not directly imply that you have to use trigonometric substitution. Check first if other techniques are applicable. The primary goal of this technique is to eliminate the radical in the integrand by using trigonometric identities that we know, such as these two, or other identities of similar nature. Now let's begin examining each three cases. For the first case, which is square root of a squared minus u squared, and for all positive a, let u equals to a sine theta, where the values of theta satisfy this inequality. Then taking the derivative of u, we will obtain a cosine theta d theta, and then we will substitute a sine theta to the variable u to obtain a cosine theta. The corresponding triangle for this case is this one. Now let's move on to the second case, which is square root of a squared plus u squared. And again, for all positive a, let u equals a tangent theta, where the values of theta lies within this domain. Then we take the derivative of a tangent theta to obtain a secant squared theta, d theta. And we will substitute again a tangent theta to the variable u and obtain a secant theta. The corresponding triangle for this case is this one. Next, for the last case, which is square root of u squared minus a squared, and again for all positive a, we will let u equals to a secant theta, where the values of theta satisfy these inequalities. Then taking the derivative of u, we will obtain a secant theta, tangent theta, d theta. And then we will substitute a secant theta to the variable u to obtain a tangent theta. The corresponding triangle for this case or form is this one. Now let's try to solve problem number 1. Evaluate the integral 1 over quantity x minus 1/2 times the square root of x squared minus x minus 1 with respect to x. First, we have to manipulate the radicand by means of completing the square. So we obtain this expression, and then after simplifying it, we will obtain this. And next step, we will factor out 1/4 to get this expression. And as you can see, 4x squared minus 4x plus 1 is a perfect square. So we can represent it as a quantity 2x minus 1 squared. Next step is we're going to substitute this expression to our original radicand to obtain this integral. And as you can see, the radical expression here looks something like square root of u squared minus a squared. And from that, we can draw some connections and deduce that a is equals to square root of 5 and u is equals to 2x minus 1, which is also equals to square root of 5 secant theta, where the values of theta satisfy these inequalities. Next step is we'll find an expression to substitute for x minus 1/2. And we can easily do that by manipulating this equation. After some manipulation, we will obtain this expression. X minus 1/2 is equals to square root of 5 over 2 secant theta. So we found something to substitute for x minus 1/2. Now we should find something for dx. And we can do that by taking the derivative of x. So after taking its derivative, we will obtain square root of 5 over 2 secant theta tangent theta d theta. And the last step is we will substitute square root of 5 secant theta to the quantity 2x minus 1, to the quantity 2x minus 1. And after that, we will obtain square root of 5 tangent theta. Now that we have all we need, we will now substitute all this to our original integral to obtain a new integral. After substitution, we will obtain this integral. And as you can see, we can cancel out secant theta, tangent theta, and square root of 5 over 2. The only thing that is left is square root of 5 over 2, which we can reciprocate and move out of the integral to obtain this. And after evaluating it, we will obtain 2 square root of 5 over 5 theta plus c. However, our original integral is written in terms of x. So we have to convert theta back to x by referring to the right triangle formed in this substitution. Now let's illustrate our reference triangle. So here it is. And based on this, we can deduce that cosine of theta is equals to square root of 5 over 2x minus 1. And by taking the inverse cosine of that equation in both sides, we will obtain theta is equals to inverse cosine of square root of 5 over 2x minus 1. Now we can use this expression to substitute for theta to obtain our final answer. So our integral is equals to square root of 5 over 5 inverse cosine of square root of 5 over 2x minus 1 plus c. And that is our final answer for problem number 1. Now let's try to solve problem number 2. Evaluate the integral of e raised to x over e raised to 2x plus quantity e raised to x minus 3 squared with respect to x. First step is we let v equals to e raised to x and dv equals e raised to x dx. And then after that, we will obtain this integral. Next step is we will expand this quadratic to obtain this. And from here, we will employ completing the square to obtain our next integral. So let's see. First, we will divide the middle term by 2 to obtain negative 3. And then square that to get 9. And then divide it again by the coefficient of b squared, which is 2. So we obtain 9 over 2. And then we add and subtract 9 over 2 to this polynomial. And afterwards, we will factor out. I will factor out 1/2 to obtain this polynomial 4b squared minus 12b plus 18. I'm going to ignore plus 9 minus 9 because they're just equal to 0. So from here, we will obtain this integral. And since 18 could be broken down into 9 plus 9, and 9 together with these two terms forms a perfect square, which can be represented as 2v minus 3 squared. We will now obtain this integral. And now we have this integral. Notice that the denominator looks similar to the form square root of u squared plus a squared. And even though it has no radical, we can still apply the normal process of trig substitution. So let's do just that. Let a equals 3 and u equals to 2v minus 3, which is also equals to 3 tangent theta, where theta lies within this domain. And then we find an equation for v, which is 3 half tangent theta plus 3 half. And from that, we will take its derivative to obtain dv, which is 3 half secant squared theta d theta. And afterwards, we will substitute 3 tangent theta to the quantity 2v minus 3 to obtain this 9 secant squared theta. And after substitution, we will obtain this integral. And as you can see, we can cancel secant squared theta and 2. While this 3 over 9 can be simplified as 1/3. So now we have this integral. And after evaluating it, we will obtain 1/3 theta plus c. However, our original integral is written in terms of v. So we have to convert theta back to variable v. And we do that by referring to the right triangle. So here's our reference triangle. And from this, we can see that tangent of theta is 2v minus 3 over 3. And by taking the inverse tangent of that, we will obtain theta equals to inverse tangent of 2v minus 3 over 3. Also recall that in the beginning, we let v equals to e raised to x. So we will convert it back again to e raised to x. And now we obtain our final answer to problem number 2. Now let's try to solve the last problem. Evaluate the integral sinh cube of x times cos of x all over square root of sinh raised to 6 of x plus sinh raised to 5 of x plus sinh raised to 4 of x with respect to x. First, we can factor out square root of sinh raised to 4 of x out of this radical expression. And since square root of sinh raised to 4 is just sinh squared, we will obtain this expression. That's why there's sinh squared there. There should be an x here. And then as you can see, we can cancel this out. And this one will become 1. And thus we obtain this expression. Now we will substitute that integrand to our integral. And from here we can let v equals to sinh x and dv is equals to cos x. So after substituting it, we will obtain this integral. From here, we can employ completing the square to manipulate this integral. Although in this slide, they use a different method, I will still discuss completing the square. So we complete the square by dividing the coefficient of the middle term by 2. So we obtain 1/2 and then we square that. We get 1/4 and then we divide it again by the coefficient of this squared, which is just 1. So we still get 1/4 and then we add and subtract 1/4. So we obtain u squared plus u plus 1/4 plus 3/4 because 1 minus 1/4 is 3/4. After that, we will factor out 1/4 to obtain square root of 1/4 times quantity of 4u squared plus 4u plus 4. And then after that, we can take the square root of 1/4, which is just 1/2, and reciprocate it so that 2 will go to the numerator. But here, they use a different method. They multiply the numerator and denominator by 2. And since 2 can be rewritten as the square root of 4, you can put 4 inside the radical. And then after distributing it, we will obtain the same integral. As you can see, there's 2 in the numerator, and the radical expression is still 4v squared plus 4v plus 4. And now, notice that 4 can be written as 1 plus 3, where 3 together with these two terms, 4v squared plus 4v, they will form a perfect square, which can be written as 2v plus 1 squared, or quantity 2v plus 1 squared. So we can rewrite this integral as this. Observe that the denominator of this integral looks similar to the form square root of u squared plus a squared. So based on that, we can deduce that a is equals to square root of 3 and u is equals to 2v plus 1. And since it is of the form u squared plus a squared, we can let u equals to a tangent theta, where a is equals to square root of 3. And the values of theta lies within this domain. Now we have to find an expression for v, for the variable v, and we can obtain that by manipulating this equation. We first divide both sides by 2, and then subtract 1/2 to both sides to obtain this equation. After that, we have to find an expression for dv, and we can obtain that by taking the derivative of v with respect to theta. And after that, we will obtain this square root of 3 over 2 secant squared theta d theta. Lastly, we have to substitute square root of 3 tangent theta to the quantity 2v plus 1. And after that, we will obtain this square root of 3 secant theta. Now that we have all we need, we can now substitute these expressions to obtain this integral. And as you can see, we can cancel out secant theta, and this exponent will become 1. We can also cancel 2, and then after that, we will obtain this integral. Next step is we will distribute secant theta to obtain this integral. This one is fairly easy because we know that the integral of secant theta tangent theta is just secant theta, and the integral of secant theta is natural log of secant theta plus tangent theta. However, recall that our original integral before is written in terms of v, so we have to convert theta back to variable v, and then convert that v back to sinh x. So let's first convert it back to v by referring to our reference triangle. Here's our reference triangle, and from here, we can easily see that secant theta is equals to this expression divided by square root of 3, and tangent theta is equals to 2v plus 1 over square root of 3. And we, from here, we will substitute these expressions to our trigonometric functions to obtain this integral. We can simplify it by cancelling square root of 3, and after that, we will obtain this expression, which is written in terms of v. Now we have to convert it back to sinh x, since we let v equals to sinh x in the beginning. So we have to substitute sinh x to every variable v. And after that, we will obtain the final answer for our last problem. That's all. Thank you very much and good luck to our Math 22 exam.